Good afternoon, everyone. I welcome you all to the course of heat transfer. In the last class, we have discussed related to some problems wherein we have seen all three modes of heat transfer. In today's class, we will discuss a three-dimensional differential equation of heat conduction in Cartesian coordinate. This is very important from the point of your examination. Now, before we proceed, I will tell you what we are going to do in this derivation part. So we have considered a small element of a cube whose dimensions are dx, dy, and dz in x, y, and z directions respectively. I will be considering the amount of heat that is flowing in x direction, that is denoted with qx, the amount of heat that is leaving the element in x direction, that is qx plus dx. Similarly, qy is the amount of heat that is entering in y direction. Qy plus dy is amount of heat that is leaving in y direction. Similar is the case with z direction. Qz is entering and qz plus dz is leaving the element. Now, if I ask you what is the volume of this element, it is nothing but dx into dy into dz. Now, what I will do is I will consider the net amount of heat that is conducted in the element in x direction, in y direction, as well as in z direction. That constitutes a three-dimension. Now, how to calculate the amount of heat conducted in x direction? That is nothing but qx, which is nothing but influx, and qx plus dx, that is efflux. If I take the difference between qx influx and efflux in the x direction, that gives me the net amount of heat that is conducted in the x direction. Similar is the case with y direction as well as z direction. Let us see how to do it. Now, here again we have considered the conservation of energy of the first law of thermodynamics, which is del Q is equals to dW plus del Q is equals to du plus del W. Now, del Q is nothing but heat conducted, net heat conducted into the element plus internal heat generation. Du is change in internal energy, and del W term is missing because the amount of work done is negligible compared to the change in internal energy as well as heat generated and heat conducted considered together. Now, that term is neglected. Now, considering the first term, net heat conducted into the element, as I told you, we will be considering x direction, y direction, as well as z direction. Now, in x direction, I told you qx is the amount of heat that is getting into the element. Qx plus dx is the amount of heat that is flowing out of the element. The element is dx, dy, dz. That is the volume. Now, what is the net heat transferred in x direction? Influx minus efflux. So qx minus qx plus dx, where qx plus dx is qx plus dou by dou x of qx into dx. If you solve for this, you will be getting kx into dx dy dz into dou square t upon dou x square, where this dx dy dz is nothing but the volume, and kx is the thermal conductivity in x direction. Similar is the case with y direction. Ky is the thermal conductivity in y direction. Same is the case with z direction. Okay. Now, what is the net heat that is conducted? It is nothing but, if I take dx dy dz common, it is kx into dou square t upon dou x square, ky into dou square t upon dou y square, kz into dou square t upon dou z square, multiplied by dx dy dz. Correct? Now, second part is the amount of heat generated. Now, if we assume Q dot is the internal heat generation per unit volume, please underline this word, per unit volume. Now, what is the total energy, heat energy generated within the volume? It is Q dot multiplied by volume. Now, what is the volume? Dx dy into dz. So, second term is over. Next term is rate of change of internal energy. Now that we know, du is nothing but mCp into dt by dt. Now m can be written as density into volume. Now what is the volume? We have discussed dx, dy and dz. So it can be written as rho dx, dy, dz Cp into dt by dt. Now if you put all the expressions in an equation, you will be getting expression like this: kx into dou square t upon dou x square plus ky into dou square t upon dou y square plus kz into dou square t upon dou z square plus q is equals to rho into Cp into dou t by dou t. Okay. Now for isotropic material, what do you mean by isotropic material? If you consider a material whose properties are same at a particular point in all directions, that is considered to be an isotropic material. What is that? At a point, if the properties in any direction, if they are same, that is isotropic material. Now, if you consider the material to be isotropic, it means at that element, the value of kx is equals to ky is equals to kz. That is equivalent to k. And if I take that and if I divide it to the above obtained expression, I will be getting dou square t upon dou x square plus dou square t upon dou y square plus dou square t upon dou z square plus q by k is equals to 1 over alpha into dou t by dou t. Now what is this alpha? Alpha is nothing but k over rho into Cp. That is termed as thermal diffusivity. Now your thermal diffusivity indicates how fast the heat is propagating. How fast the heat is propagating. It means that if greater is the value of alpha, lesser is the time taken. Now this expression is considered as three-dimensional heat conduction equation in Cartesian coordinate. Now we have some special cases. If in the general heat conduction equation, if we assume there is no heat generation, then Q dot term will be 0. We will be getting this expression, which is called as Fourier equation, or it is also called as diffusion equation. Next, for steady state, whenever we consider steady state, the change in property of temperature with respect to time should be 0. In that case, this whole term will be 0. And if we consider with heat generation, this is the expression. And this is called as Poisson's equation. And if we consider no heat generation and steady state, so this term is 0. At the same time, Q dot is also 0. Now we get simply dou square t upon dou x square plus dou square t upon dou y square plus dou square t upon dou z square equals to 0, which is nothing but a Laplace equation. You know that. If you consider this is the expression for Cartesian coordinate, for cylindrical coordinate, in a similar way we can derive for a cylindrical coordinate. We have considered a small element as shown in the figure. Okay. Now we have three directions. One is tangential direction, that is phi direction or theta direction. Next one is axial direction, that is z direction. So qz plus dz, that is axial direction. One more is radial direction, qr and qr plus dr. Now the derivation part is similar to the Cartesian coordinate. So qr is the entering, qr plus dr is leaving in radial direction. q phi is entering and q phi plus d phi is leaving in tangential direction. qz is entering and qz plus dz is leaving in axial direction. Now if you solve as same as the previous steps, you will be getting this as the final expression. So you will be asked either Cartesian coordinate or cylindrical coordinate alternatively. These two are very important from the point of your examination. Next, we come across initial and boundary conditions. Now, in order to analyze something, we need to give some conditions. They are called as, if we apply at the boundaries of the system, they are called as boundary conditions. If it is applied with respect to time, they are called as initial conditions. Now we have three types of boundary conditions. Boundary condition of first kind is also called as Dirichlet boundary condition, where we will be mentioning the temperature, particular values at the boundaries. For example, if you consider this at x equals to 0, what is the temperature? T1. At x equals to say L, what is temperature? T2. Now the same thing is applied here. Okay. Second is boundary condition of second kind or Newman boundary condition. Here, instead of absolute values, we will be mentioning the gradients. It could be heat flux. It could be temperature gradient. Okay. Next is the combined form, which includes Dirichlet as well as Newman type of boundary condition. And the expression is as follows. Now, once we understand the boundary conditions, we can apply a one-dimensional steady state heat conduction without considering the heat generation. And this is through a plane wall. Now we have noticed the one-dimensional heat conduction equation without heat generation for a steady state will d square t upon dx square is 0. Okay. Now, if we integrate for the first time, we get dt by dx equals to c1. Integrate one more time, you get the equation for t in terms of c1x plus c2. Now you need to apply the boundary condition and get the expression for dt by dx. That will be discussed as follows. Now we have assumed at x equals to 0, temperature is T1, and x equals to L, temperature is T2. Now your temperature in terms of unknowns or constants is T is equals to C1x plus C2. Now, after applying boundary conditions, if you get the values of C1 and C2, your C2 is nothing but T1 and C1 is nothing but T2 minus T1 divided by L. Now, put C2 and C1 in T equation. Okay, because you are looking for temperature profile, correct? Next, so T will be T2 minus T1 by L into X, that is C1x plus C2. C2 is nothing but T1. Now, out of this, if you get dt by dx, if you differentiate this equation with respect to x, that is your dt by dx. Now, if you differentiate this equation with respect to x, so this term goes to 0 independent of x. So you left with the coefficient of this x term. So q can be written as minus ka into dt by dx. Correct? Now dt by dx is nothing but t2 minus t1 divided by n. You know that. So q is equals to minus ka into t2 minus t1 divided by n. Or it can also be written as plus ka divided by l into t1 minus t2. Both are same. Now here you got q is equals to delta t over something. This term is nothing but resistance, in which case plain slab, and this is nothing but conductive resistance in plain slab. Let us consider a problem. Calculate the rate of heat loss from a red brick wall of length 5 meter, height 4 meter, and thickness is 0.25. The temperature of inner surface is 110 degrees Celsius and outer is 40 degrees Celsius. Thermal conductivity of the brick is given, which is 0.7 watt per meter Kelvin. You also need to calculate the temperature at interior point at a distance of 20 centimeter from the inner wall. Okay, fine. Now, let us understand what is given. There is a wall, its length is 5 meter and height is 4 meter. Now, the area of heat transfer is 5 by 4, which is 20 meters square, and the thickness is 0.25 meter. Your inner temperature is 110 and outer temperature is 40 degrees Celsius, and K value for the material is given. Now, the problem is simple. If you apply the conduction equation, Q is equals to Ka into T1 minus T2 divided by L, where L is thickness 0.25, K is thermal conductivity, A is area perpendicular to which the heat is flowing. Now that is 20. If you substitute the values, you will be getting 3.92 kilowatts. Now the second question is, he has asked you to calculate the temperature at a point which is 20 centimeter from the inner surface. It means that at this point you have calculated at a distance or at a thickness of 0.25. If this is 0.2, what is the T2 temperature? That is what the question is. Now Q remains same because it is a steady state. Q remains same. So Q is equals to Ka into T1 minus, this is the unknown temperature, and he has asked you to calculate at 20 centimeter distance. So this becomes your thickness. If it is asked at midpoint, this could be 12.5 because total thickness is 25 centimeter. Okay, if you substitute the value for Q as 3.92 kilowatt and rest all the values, you will be getting a temperature which is obviously greater than the surface temperature, which is 54. Okay. Now, if you consider the one-dimensional heat conduction for cylindrical coordinate, the expression is this. In a similar way, if you integrate and get the expression for temperature, it is C1 ln R plus C2. And if you apply the boundary conditions at R equals to R1, your temperature is T1, and at R equals to R2, the temperature is T2. Then you will be getting C1 is equals to T1 minus T2 divided by ln of R1 by R. How did you get this? So at T equals to T1, what is R value? R1. Put R equals to R1. So T is equals to T1, R is equals to R1, C1 ln R1 plus C2, and T2 is equals to C1 ln R2 plus C2. Now if you take the difference, so T1 minus T2 is nothing but C1 ln R1 minus ln R2, which is nothing but ln R1 by R2. If you substitute for the value of C1 and C2, you will be getting this expression. This is the temperature distribution. Similar is the case with sphere. So where the resistance is 4 pi k R1 R2 into delta T divided by R2 minus R1. So that is the heat conduction equation, and if you take the resistance, so this term is the resistance R2 minus R1 divided by 4 pi k, one sec, R2 minus R1 divided by 4 pi k, R1 R2 is the conductive resistance in case of sphere, where R2 is the external radius of the sphere, R1 is the internal radius of the sphere. I think we have done this in heat transfer lab. Next, coming to the composite work. Now, what do you mean by composite work? If you combine two or more material of different properties, and if you consider them to be one by pressing each other, by combining each other, then that whole material is considered as composite material or composite work. Now in this case, we have three different materials of thermal conductivity, K1, K2 and K3 respectively. Now this is nothing but conductive resistance and conductive resistance. Now for a heat to flow from this point to this point, these acts as the barrier or the resistances. Now what is the value? So for this, if this is of thickness L1, L1 by Ka, L2 by Ka and L3 by Ka. So these are called as conductive resistances in case of plain slab, where L is the thickness, K is the thermal conductivity and A is the area normal to the direction of heat flow. If nothing is mentioned in the problem, you can assume area to be 1. In some cases, the material is placed in this way, where the resistances are parallel in nature. Now, how to calculate equivalent resistance? 1 over R1 plus 1 over R2 is equals to 1 upon R equivalent. So that will be solved in one of the problems that we are going to consider. Now let us consider a problem on composite slab. We have, let us go with the problem. A wall is constructed of several layers. The first layer is consisting of a brick with K is equals to 0.66. Thickness is 25 centimeter. Second is mortar. Thickness is 2.5 centimeter and K value is 0.7. Third is a limestone. Thickness is 10 centimeter. K value is 0.66. And outer layer is plaster. Thickness is 1.25 centimeter and K value is 0.7 watt per meter Kelvin. Exterior of the wall fluid layer are 5.8 and 11.6. It means that we need to consider the convective heat transfer also. So he has given for the interior as well as exterior, it means H interior is 5.8, H exterior is 11.6. So we have 4 materials here, and we should also consider internal convective resistance as well as external convective resistance. So total we have 6 resistances, 2 convective resistances and 4 conductive resistances. So what you need to find? Overall heat transfer coefficient, that is U, we have discussed, that is nothing but 1 over summation of R, where R is the summation of all the resistances, plus it must be added with, multiplied with area. Next, overall thermal resistance per meter square. So you got U here, overall heat transfer. If you take the reciprocal of that, it is overall resistance. Then rate of heat transfer per meter square. He has not mentioned anything related to area. You can assume area to be 1, and he has asked heat transfer per meter square. If the interior of the room is 26 and exterior is -7 degrees Celsius. So let us have the look of the problem. So as I mentioned, we have 4 different materials. The first one is a brick, mortar, limestone as well as plaster. Along with these 4, we have interior convective resistance, exterior convective resistance. So total 6 resistances, R1 to R6, where R1 and R6 are convective resistances, R2, R3, R4 and R5 are conductive resistances. Now, area we need to consider to be 1. So R1 is 1 over HA, because we know that convective resistance is 1 over HA, area is 1, H at the interior surface is 5.8. So that gives us 0.1724. Unit is degree Celsius per watt or Kelvin per watt. Similarly, R2 is L over Ka, area is 1, L is given, K is given. You can consider R2 to be 0.378. Similarly, R3, R4 as well as R5 as 0.0357, 0.1515, 0.0178 Kelvin per watt respectively. Next, R6 is again convective resistance. So convective heat transfer at the exterior side is given. So you can calculate R6 as 0.0862 Kelvin per watt. Now overall heat transfer coefficient is 1 over area into summation of R. So area is 1 and this is the summation. So that gives you a value of 1.18. The unit is watt per meter square Kelvin. Next, overall thermal resistance is 1 over U. If you do, you will be getting 0.8424. Then heat transfer he has asked. So total temperature difference divided by total resistance. So internal it is 26, external -7. You need to take the difference. So this will get added. This divided by total resistance is 0.8424, which gives you 39.17 watt per meter square. This is the heat transfer or heat flux, we can say, because we are considering area to be 1. Next, he has asked you, what is the temperature, intermediate temperature at the junction between mortar and limestone. So we have mortar here and limestone here. He has asked you to calculate this temperature, intermediate temperature. Now how to do this? Now we will consider this as well as this resistance. So T1 minus, we don't know this temperature, T divided by these 3 resistances should be equated to Q, and Q we know, we calculated just now, 39.17. So if we equate Q equals to 39.17 and take the temperature 26 minus the unknown temperature T and divide it by these 3 resistances. Why these 3 only? Because they are the barriers for the heat flow at that point. So you get a temperature of 3 degrees Celsius. We will stop here, and in next class we will see some other problems pertaining to composite, cylinder as well as sphere. Thank you.